In this video, we will again continue our discussion of the Algebra 2 final exam review. This time we're starting with the factoring questions. So I'm going to be looking at number 22, 24, and 26, and the techniques that we complete here should be similar to what you'll see in your odd-numbered problems. But before we begin, let me just remind you of the factoring techniques that we practiced extensively in class. There really are just two or three of them. The first one is what we call a Gcf. So we can factor greatest common factors out of a term, and I think we'll see that with question number 22. We will also see what we call standard trinomials. We'll talk about those. And then also non-standard trinomials. Those are the most common. Occasionally we do have a technique called factor by grouping. That's for 4 terms. And then also we have other special cases. And those special cases, at least in this class, were the sum and difference of cubes. So let's talk about number 22 for a moment. A lot of times with only 2 terms present, we tend to only factor with the greatest common factor. There are some exceptions to that, but many times this is all we can do. And what we're trying to find are terms that are common to both of these, I should say elements that are common to both of these terms. In this case, both of these terms contain a series of b values, and both of them could actually give up 2 b values. So in essence, when we're factoring, we're trying to divide these common terms from one another. And if I could divide both of these terms by b squared, what I would like for you to do is list that b squared as a factor in front of a grouping symbol, and then indicate what's left over after you do factor or divide that common factor from each term. So if we look at these 2 problems individually, b cubed divided by b squared, well, that's 3 b values in a row divided by 2 b values. That's going to leave me with 1 b value. In this second problem over here, 4b squared divided by b squared, well, b squareds will cancel. Both b values in the numerator and the denominator will disappear, and we're left with plus 4. And this would be a good factored result. This factoring technique leads us to methods that we use to solve equations in this class as well as in our college algebra and pre-calculus courses. With number 24, we have 3 terms. So this is a trinomial, and we have lots of different ways that we can factor it. But before we go factoring using any trinomial methods, we should always be on the lookout for greatest common factors, GCFs. And we actually have that here. Each of these 3 terms can be divided by the number 2. Now, since I am factoring out or dividing by the number 2, I want to list that in front of a group of parentheses, and then I'll show what's left over after we complete that division for each term. In this mini problem, 2n squared divided by 2 is going to leave us with n squared. In the middle problem, 6n squared divided by 2 is going to leave us with 3n. And then finally, at the very end, we have negative 20 divided by 2, which is simply negative 10. And sometimes this is a good and final answer, but let's not forget that our instructions for this set said to factor each problem completely. So what that tells me is that before we commit to this as a final answer, we should double check the factor results that remain and consider factoring them further. Now there are no more common factors in these 3 terms, but what I do have is a standard trinomial. And I know that this is a standard trinomial because the number in front of the variable squared is just the number 1. Now I'm not looking at that 2 anymore. I've already factored that out, and I'm temporarily ignoring it. What I'm looking at is the letter in front of this trinomial, n squared, and since there's the number 1 that's implied to be there, I'm going to call this a standard trinomial. And what I'm hoping to do with this standard trinomials is to find 2 numbers that multiply, in this case, to equal 10, but the same 2 numbers add or subtract to equal 3. And actually, I should say this, they multiply to equal negative 10, not just 10, but negative 10. And they add or subtract to equal 3, because what I'm hoping is going to happen is that I'll be able to factor this trinomial into a pair of binomials. Now this 2 is going to come down because it was factored out originally, so it needs to remain with the problem. But I'm hoping to find, again, two numbers that meet these criteria. And again, since this is a standard trinomial, we leave the n values at the beginning of each of these binomial groups. And if we can find two numbers that multiply to make negative 10, that add or subtract to equal 3, then we're going to be in pretty good shape. Now, there could be many numbers that multiply to make 10. For example, 1 times 10, 2 times 5. Lots of different pairs multiply to make 10. Maybe I should list them this way. 1 and 10, 2 and 5. But only one of those pairs, if possible, will add or subtract to make 3. And as it turns out, if I had a negative 2 times positive 5, that would equal negative 10. And then also negative 2 plus that positive 5 would equal positive 3. So I think we found a pair of numbers that's going to work. So along with this n and this n, I'm going to report the number positive 5 and the number negative 3. Oops, sorry, negative 2. Now it doesn't really matter which order you report these numbers in. N minus 2 with an n plus 5 would be just as fine as a final answer. Now that may seem strange as a result or strange as a process, but if you recall, we can check our work by multiplying this back together. And so I've distributed 2 into this first group. It doesn't go into both groups, it only goes into the first parentheses group when distributing. And now I've FOILed this next step. And lastly, I'll combine like terms, these two in the middle. What we should end up with is the same result as the equivalent value in our beginning problem. Now, this is not the same as what we started with. However, if we were to distribute this 2 at the very beginning, oops, sorry, I guess we did start with that above. I forgot we had this problem right above it. So certainly this does match what we had started with. And so that's a good way to check our work. This answer was correct, 2 times n minus 2 times n plus 5, because when FOILed, or when distributed back together, it equals our original problem. Let's try one more example, number 26. In this case, we only have 2 terms, so you might be thinking that a common factor would be the technique or method here. That's not necessarily the case, because this r squared and 49 without a variable r don't have a common factor. But you may recognize that there is a term missing, and we technically have in the middle a 0r term. We don't usually write that because 0 times r is 0, and that term effectively disappears. But if I do rewrite the original problem with 0r, now this is starting to look a little bit like a standard trinomial. And again, with a standard trinomial, we're looking for 2 numbers that multiply to equal the last term, that add or subtract to make the middle term. So, can you find 2 numbers that multiply to make negative 49, that add or subtract to equal 0? Well, as it turns out, the number 7 times 7 will equal 49. In fact, negative 7 times positive 7 equals negative 49. Moreover, negative 7 plus 7 equals 0. So I do believe we have found a factored result. In fact, the more you practice, the more you'll recognize this pattern and how it factors so easily. It actually has a special name. It's called the difference of 2 squares. So anytime we have an expression that's in this format, we can factor it very quickly into its final result without showing much work, if any at all. I think that's a good stopping point for this video. If you've got questions on problems 21 through 26, please let me know. Thanks for watching.